This time I want to talk about characteristic quantities. You may have heard about universal constants in physics, such as Planck constant, denoted by h, or speed of light, c, or universal gravitational constant, g. These quantities appear in different branches of physics. Naturally, the speed of light, c, appears in relativity. The Planck constant, h, appears in quantum mechanics, and g appears in gravitation. Of course, all of these, h, c, and g, appear in quantum gravity. There are other universal constants in physics. Let's take a look at these tables. In the first table, we see Planck constant, speed of light, gravitational constant, and epsilon 0 vacuum permittivity, mu 0 vacuum permeability, electron charge E, and electron mass m. You can see that their dimensions and their values in SI units. In the second table, you see some dimensionless universal constant. Alpha, fine structure constant, which is defined as E2 over 2 epsilon 0 hc, which appears in atomic physics, or lambda, the cosmological constant. The coupling constant for the strong force, alpha s, or the number of macroscopic special dimension, d, which is 3. Fine structure constant is 1 over 137, and cosmological constant is 10 to the power minus 22. We may choose any of dimensional constants, universal dimensional constants, as independent dimensions. And upon changing system of units, we can set any of them to be equal to 1. For example, we can set c, speed of light, to be equal to 1. In Gaussian system of units, epsilon 0 and mu 0 are equal to 1. But the values of physical dimensionless quantities does not depend on the system of units. Their values are the same for all system of units. In physics context, we may sometimes talk about characteristic quantities with various dimensions. For example, characteristic length or length scale, characteristic mass, characteristic time, or characteristic energy, and so on. In any problem, these characteristic quantities may arise naturally. For example, in a fluid flowing in a long circular pipe, the radius of cylindrical pipe is the characteristic length of the problem. R is the characteristic length of the problem. If in a similar problem, where the cross-section of the duct is a rectangle of the sides A and B, there are two characteristic lengths. A and B, the sides of rectangle. A square has one characteristic length. In fact, ideal square has one characteristic length. Most real ducts are rounded squares. There are two characteristic lengths, the side length and the radius of the arc. Or a rounded rectangle has three characteristic lengths, at least three characteristic lengths, A, B, and the radius of the arc. There may be some defects. Then there are more characteristic lengths. So, in some cases, there are particular lengths which we may choose as characteristic lengths, or in some cases there is not a characteristic length. But with the dimensional parameters of the system, we may construct a length, time, or any other dimensional quantity. For example, in quantum gravity, where we have G, C, H, we may construct a characteristic length L sub p, which is defined as hg over 2 pi c to the power 3, which is known as Planck length or Planck scale. There are various length scales in physics. Planck length scale may be the least length up to known laws of physics. We can determine a position. Some most known characteristic lengths are Planck scale, Planck length, de Broglie wavelength, mean free path, and etc. If we are dealing with a macroscopic system, it's not reasonable that the characteristic length is microscopic one. Characteristic length, time, energy, and etc. are the important dimension that define the scale of the physical system. Characteristic quantities may appear naturally in our problem, or may be a combination of the model parameters. Without any detailed calculations, characteristic quantities give new insights into the scale of the system. There are dimensionless quantities in different areas of physics. For example, in fluid mechanics, with the density of fluid, rho, its velocity, u, and characteristic length, L, viscosity, mu, and pressure, P, we may construct dimensionless quantities such as Reynolds number, or Euler number, or some other dimensionless quantities. In summary, there are some universal constants in physics. Despite their name, universal constants, they are not constant. Their values depend on the system of units. We may choose the dimension of any of them as an independent dimension, and upon changing the units, we can set any of them to be 1. There are some universal dimensionless constants in physics. Their values are the same for all system of units. There are some dimensionless quantities in different areas of physics that are not constant. They depend on the model parameters, such as Reynolds number, Euler number, and so on. Characteristic quantities may appear naturally in our problems, or may be a combination of the model parameters. Anyhow, they give an insight into the model.